So welcome everyone to the CPPC seminar. Today's speaker is Sato from Yokohama National University. Joe has been working on a range of BSM topics, specifically on neutrino physics, charge lepton, flavor violation, on extra-dimensional models. But today he will be talking about something which we have been discussing here as well. A lot was about singularities, infrared singularities, and specifically the T-channel singularity. I'm looking forward to a very interesting talk to hear about an analytic prescription for the T-channel singularity. So yeah, please, Joel.
Yes, thanks for introduction, Michael. So Michael is called Michael or Michael?
Yeah, Michael is good.
Michael is okay, thanks. So I met Michael 20 years ago when he was a TUM PhD student while I was a visiting researcher at TUM, Technische Universität der München. So, and today, anyway, I thank the organizer for me to give a seminar at Sydney. So in this year, I have enough grants, so I'd like to visit Sydney directly. But yeah, anyway, next chance I'll see. So today I would like to talk about a kind of singularity divergence in amplitude. So this title is taken from our latest paper with authors here. So and today's talk is based on works with these people. And this title is taken from the latest paper with these people whose names are written in boldface. So let me start. Okay. So plan of talk is here. So first one third part is a little bit general motivation to consider this kind of stuff. And the second part is my motivation to consider this kind of singularity divergence. And the last part, last one third consists from the latest paper. So I'm very sorry that my abstract is taken from the latest paper, but topic is rather wide. And I'm not good at English, so if you find something wrong or something misleading, please let me know. I will try to answer quickly. So let me start my talk. So first, I'd like to give a general motivation to consider this kind of stuff, divergence, and the review on the treatment of this kind of singularities and how to make use of these singularities or how to interpret these singularities in general. So as you know, it is very important to consider the scattering process. Since all standard models are checked by the scattering process, and also to check standard model means, in some sense, to explore new physics beyond the standard model, and this kind of stuff is also given via the scattering process. And scattering process means there is a mediator particles depicted like this. So sometimes we consider more complicated process, but in general, we consider, in most cases, we consider two process. So please see the time flow from left to right in these pictures, in these Feynman diagrams. So the left one is called S-channel type. So there are two particles joined at some point and create a mediator particle in this way, and this mediator particle decays into the final state. On the other hand, the right-hand type is called T-channel or U-channel type diagrams. So, and this in this case, the initial particles decay into two particles in each vertex, and one of these particles meet at some point in this way. And this is called a T-channel type. And to calculate these amplitudes, we need a propagator for these mediator particles. And this mediator particles propagator is always given by this form. And here, this regulator I is very important. We have many kinds of regulators, but by demanding the causality of the process, it is known that we have to give the propagate regulator in this way, plus I epsilon here. And if the mediator particle is off-shell or vertical, then it means that p square minus m square is not zero. So always the propagator is finite. On the other hand, if this mediator is on-shell, that is real particle, then it means the p square is equal to m square. So the propagator will be divergent in this way. So after the calculation, epsilon must be taken to be zero. So naively, there is a divergence on scattering process. So how to deal with this divergence is very important. This is a general view of this talk. So from now, let me explain this divergence in order. So first, I would like to mention about a standard type. This standard type and divergence can be interpreted in this way. So here in the intermediate particle, if mediator is real particle, then this process can be interpreted in this way. That is, first, two particles meet to create one mediator particle here. And this is indeed a real particle. So it flies to some time. And then it decays into two particles here. And this creation process is often called inverse decay. And of course, this is the final process, is a decaying process. So the process with the divergence is interpreted as first there is inverse decay, that is the creation of intermediate mediator particle, and then mediator particle decays into two particles. It means that mediator is always unstable. So as I will explain in more detail, this is not a real singularity, but it is regulated in a very clear manner. But in this talk, I will use the singularity or divergence. I dare to use this terminology in the analogy with T-channel divergence. On the contrary, T-channel process can be T-channel divergence can be interpreted in this way. So here is, can you see my cursor? All right. So here is, sorry, intermediate particle can be a real. It means that first decay in one of initial particle decays into two real particles. Then one of these real particles can meet with another initial particle here. Then it creates a final state, final particle here. So the existence of pole of T-channel means there is first decay of some particle, and then there is an inverse decay, that is a creation of particle here. And in this case, a mediator can be stable. Of course, it can be unstable, but it can be stable. And if the particle is stable, then this divergence may be a very disastrous. This is a brief review of S-channel pole and T-channel pole. And from now on, I will explain in more details about S-channel pole and T-channel pole, S-channel divergence and T-channel divergence. So as I said, I will dare to use the S-channel singularity or S-channel divergence. But this is very clearly regulated by the reason I will mention. So as I told you that this S-channel singularity occurs when the initial particle A and B creates the mediator particle in real. And this real particle can decay into another particle, or maybe, of course, C can be A and D can be B, but also mediator particle can decay into another particle. Anyway, first creating the mediator particle, intermediate states as a real particle, and then this real particle decay into another particles. This is interpretation of S-channel singularity. In this case, the propagator of the mediator particle is given at the tree level by this kind of stuff, of course. So this is a kind of tree propagator. So at one glance, there is a singularity here, since p square equal to m square, and we have to take epsilon to 0. However, by considering the one loop corrections, or of course you consider more higher loops, but naively by considering one loop corrections, it is understood that we can regulate this propagator. The reason is that since we have this kind of vertex, then as a one loop correction, we could get this kind of propagator too. So M decays into A and B, then it creates the M star here. So this is completely same process as a tree process here, M to M star. And as you know, by by taking a summation of this propagator here, the real propagator is given by this form. The propagator is modified from the I epsilon type to I m gamma type. And of course, m and gamma are finite. So automatically, in this case, the propagator is regulated by the decay constant here. So in principle, there is no divergence at all. So no singularity is here, and it is called resonance. And the example of resonance are, there are many examples of this kind of resonance. So in real physics, we can see many this kind of resonance. And probably in my sense, the most famous resonance is delta resonance. Of course, it is up to you. But as a very famous example, I would like to explain the delta resonance here. So, as you know, this resonance is predicted by these peoples about 60 years ago. So, this resonance is arise due to the interaction between ultra-high energy cosmic rays, protons, and cosmic microwave background in this way. If this cosmic ray has high energy enough, then it can create real delta particle as an intermediate state. And it decays into p pi 0, or sorry, n pi plus here. Then these high energy protons are, the information about this high energy proton is completely lost by this resonance. And from the energy of CMB and from the mass of delta particle, we can predict that. Just a moment. if the proton has a high energy higher than around 10 to the 12 electron volt, this process has a resonant behavior. That is, this amplitude is enhanced by this resonance. And it means that such a high energy proton have a very short free mean path, and hence we cannot observe such a high energy proton in the Earth. So this is this graph is taken from this side, and it is said that around 10 to the 20 electron volt square, there is a strong cut of the spectrum of high energy cosmic rays in this way. So this is the first example of the resonance in my terminology, and this is caused by the S-channel singularity. And also another example is Z-burst. So high energy cosmic neutrino can interact with the background neutrinos. And if this neutrino has a energy high enough, then it can create real Z in this way, and this Z decays into two fermions. And if there is a real Z, then the amplitude is enhanced, and at the resonance energy is predicted around 10 to the 12 electron volt, and it is predicted that a neutrino higher than this energy cannot reach to the Earth. And I will show our example later. I will use this analogy later to discuss ice cube gap. Of course, I will explain ice cube gap briefly later. On the other hand, T-channel singularity is really a singularity in some case. So as I told you, S-channel singularity is given by two processes. First, decay into a real particle. And one of the real particle can combined to create the final particle in this way. In this case, mediator, there is no, in this case, in principle, we do not have any regulator for the propagator. And I will show a concrete example. And there, in this, the intermediate particle is neutrinos. And in this neutrino, as you know, neutrino cannot decay into another particle, so we do not have any regulator from the decay constant. So it is a problem to consider how to deal with that. This is today's main topic. And examples, several examples are known. First example is given by Piers about 60 years ago. And in his discussion, in some case, this kind of T-channel, here is a real particle, some nucleon. And pi n star to pi n double star, considering pi n star to pi n star plus, then there is a real particle in here as an intermediate particles. And his discussion is not to point out the T-channel singularity itself, but there is often a S-channel singularity in scattering process, but this kind of S-channel scattering could be explained by T-channel singularity. This is what he wants to show. And probably and then I will give another example. This is related with the real physics, real physics. So, for example, let's consider muon collider. So recently, muon collider is really popular. So many of you are interested in muon collider too, I think. So, and muon collider, if muon is a stable particle like electron, then we do not have to care about this kind of T-channel singularity. But since muon can decay into real particles, so for example, let's consider the process mu minus 2 mu plus goes into E minus nu E bar plus W plus, right? And naive, and this process is given by this process. X is the decaying part and created particle from double boson decay. So please see this graph as mu minus 2 mu plus goes into E nu E W, right? And what is T-channel singularity is that by considering first muon decays into electron neutrino and mu neutrino in this way. And the mu neutrino can meet with mu plus to create W plus, right? This is just a gauge interaction. In this case, muon can, since mu neutrino and mu plus are energetic, so we can create real W plus. And in this case, also mu neutrino here can be a real particle. So naively, we consider the propagator here. We have a divergence proportional to 1 over epsilon. And for this process, these people says that this can be regulated by beam size. Honestly speaking, I couldn't understand their real points, so I do not mention in detail. I cannot explain details what is beam size. But they, in a real experiment, anyway, muons have a beam size, not to pure plane wave. So by considering this non-plane waveness, what do you say in English? I'm not sure. But anyway, since they are not from a real plane wave, this propagator could be regulated. They insisted so. And this is called beam size effect. And in cosmology, there are often T-channel singularity. About this, I will show concrete example in the context of our works. So since I would like to explain this process in our works, so I will use the terminology Z prime and neutrino phi. Some of you understand that Z prime is a kind of extension of gauge boson, whose mass is very light. And this phi is called myoron. So if you are familiar with neutrino mass matrix or this kind of stuff, then it is easy to understood. While if you are not familiar with this kind of stuff, please think that there is anyway some unstable particle which can decay into two neutrinos, and two neutrinos can form another very light particle here. So in this case, since there is a neutrinos, we cannot regulate by its decay constant. So there are several ideas to consider this process. One is often called thermal mass, but I can't understand anyway. For neutrino in low temperature, it cannot regulate anyway. But several people insist that. Also, some people consider the complex momentum from the unstableness of the initial particle here. So as I told you, Z prime can decay into two particles. It means that there is a decay constant in its initial momentum. So here, momentum is not real one, but complex momentum can flow here from the unstableness of the particle. And at one glance, I thought that it works, but I couldn't understand the momentum conservation comes from this kind of integral. And this formula holds only for P is real. P real only for real P. So if P is imaginary, then can we analytically continue to this delta function or not? I'm not sure. So it may work, but it may not work. I'm not sure. And many people do just ignore. Since, as I told you, this process can be decomposed into two processes, the prime decay and inverse decay for 5 microns. And these two separate independent processes are taken into account already in cosmology. So people insist that we can just ignore. Today, I would like to our approach the fourth method here, but historically, probably there are this kind of treatment has been made. So sorry, time is very strict or very rude or anyway, please control me too. So
it's okay. It's okay. We have time.
okay. So so next I would like to explain my motivation to consider this kind of singularities. So in the context of cosmology, we have examined Fermi-Eltau model to explain ice cube gap and to explain Hubble tension. Very accidentally, to explain these two anomalies in Fermi-Eltau model, very accidentally, parameter region is same to explain these two gaps. So I thought it is interesting to consider this kind of models. Incidentally, very till recently, also parameters to explain these two anomalies explains G-2 magnetic moment. But now I can't say it is interesting or not. I'm not sure. But anyway, with same parameters, we can explain these two anomalies. So I would like to briefly mention about Fermi-Eltau model and then how to explain these two gaps in terminology of resonance, standard singularity, and and how to explain Hubble tension. In this case, T-channel singularity cannot do not explain Hubble tension, but anyway, to consider Hubble tension, we need to treat T-channel singularity. And this is a direct motivation to the main topic today. So first, let me explain briefly what is Fermi-Eltau model. So we introduce some new gauge bosons, which interact with muon flavor and tau flavors. And the interaction charge is opposite between mu type and tau type. By this treatment, we can get anomaly-free models. And of course, we can construct a model with which this mass for G prime is derived from the Higgs mechanism. But in many cases, just we work with this kind of effective Lagrangian here. So as a concrete model, for example, we constructed as a linear magnet model. There are many examples. This is our example to derive this kind of new Lagrangians. And in many cases, this kind of model is motivated first to explain the neutrino mass and lepton mixing. And to generate lepton mass, if neutrino mass is Magellan type, then we need to break the lepton number. And to break lepton number, we often have a Schumann-Golson boson, which is called myeron, and depicted by phi. And its interaction is given. Its interaction with neutrino is given by this Yokohama form here. So from this Lagrangian, we can see that Z prime can decay into nu bar. This can be seen from this interaction. So Z prime here and here are two neutrinos, or here are two neutrinos, right? And also it is seen that directly from this L phi Lagrangian that phi decays into two neutrinos. And also by combining these two, it is easy to understand that we have a scattering process G prime nu to phi nu bar, or G prime nu bar to phi nu, and also G prime phi to nu nu. And in the early universe, we have to know the number density of Z, not only neutrinos, but also phi and Z prime. We have to take into account this process in Boltzmann equation. And to calculate the Boltzmann equation, we need to know the cross-section for this scattering process in principle. And in this scattering process, we have a T-channel singularity. That's a story to the road to my today's main topic. So the good point for this gauged mu minus tau symmetry is summarized here. So as I told you, there is no quantum gauge anomalies, and there is no LFB coupling as a gauge no direct lepton flavor balancing coupling in this gauge couplings. Of course, to generate neutrino mass and lepton mixings, we have to break lepton flavor. And this can be given by some other mechanism, which is related with lepton number. And then we in general have a myeron. And originally, this is considered since it can explain the muon G minus anomalies, anomalous magnetic moment. But anyway, let me explain our motivation to consider this L mu minus L term model. So first, I would like to explain what is ice cube gap. As you know, in Antarctic, at the South Pole, we have a huge detector which is called ice cube. And it can observe the very high energy cosmic neutrinos. And there are many studies what kind of source can create such a high energy neutrinos. But naively, if we can consider a PP collision or gamma P collision here, then first pions are created and pion decay into one neutrino, electron neutrino, and two muon neutrinos. And yeah, and then it flies to the Earth, it oscillates into some other flavors, and naively the content gives flavor content is given 1 to 1 to 1 here. And in this, about 10 years ago, they succeeded to observe such a high energy neutrino. So 10 to the 6 GB means 1 PeV. And this is the first result from here. And at that time, statistics is very low. So this is consistent with this kind of energy flux. And it looks no anomaly here. But many particle physicists thought that there is an anomaly here, like that. In this, there is no observation around this energy range. So how to consider this gap was many physicists are excited to explain this gap. And there are mainly three ways to explain this gap. And we took one of these approaches. That is, we introduce new interactions for neutrinos. This is essentially the same idea with Z-burst. But as I told you, to have a Z-burst, the energy range must be about 10 order of magnitude higher than neutron energy must be higher than around 10 order of magnitude. So to have a kind of Z-burst, we have to introduce much lighter intermediator here. And it is very easy to estimate how light it is, since we have to create real Z prime so that this process is enhanced. So cross-section is given by this form. And this is a kind of a standard singularity diagram. So if the initial energy becomes mz square, this intermediate mass, then this cross-section is highly enhanced in this way. And since we know the background neutrinos are almost static, so its energy is given by neutrino mass. And also to calculate the root S, we need initial energy of cosmic neutrinos. And since the resonance occurs at around 500 TeV region, so the mediator mass must be MeV scale. So as a cartoon, we can see what happens. If neutrino have this energy, then only neutrino with this energy can strongly hit with background neutrinos. So neutrinos with this energy cannot reach to ice cube, cannot reach to the Earth. While as high energy neutrinos, the cross section is quite low, so their mean free path is long enough to reach to the Earth. So we can create the gap around here. And indeed, if the prime mass is around 10 MeV, and there are 3 neutrino masses, so this is the example from normal hierarchy. In this case, around gauge coupling with given this value, we have successfully created the gap here. And this is completely mechanism is completely same as Z prime, Z bus. And instead of Z boson, Z boson, we introduce new gauge boson Z prime. So it should be called Z prime bus. And this is a kind of, this is one of example of a standard singularity. So we are interested in this kind of divergence process, which is caused by real intermediate particles. And this kind of interaction is in general called secret neutrino interaction. So this intermediate particle is not necessarily be a gauge boson, vector boson, but also can be a scalar and other particles. And many people consider similar stories. But anyway, from the resonant condition, the particle mass must be around 10 MeV. And to have sufficient cross-section, coupling must be of order 10 to the minus 4 or higher. So first, I became interested in this kind of models through the ice cube gap. And nowadays, how to interpret this diagram is difficult, but at that time, G minus 2 is more anomalous than ice-cube gap. So more people consider G minus 2 than ice-cube gap. And accidentally, to explain G minus 2, simultaneously explain ice-cube gap. So we are excited. This is the first story. And after a while, at some conference at Argentina, I find the talk given by some people who is a collaborator with Escudero. I will mention about their work briefly. Before going in detail, I would like to explain what is Hubble tension. Hubble tension is some tension between the two methods to measure Hubble constant. Tension between the value measured by just a moment. Hubble tension is the tension of Hubble constant between two methods to measure. So there are two approaches. Nowadays, there is a third approach, but at that time there is a two approach to measure Hubble constant. One is called indirect approach. So to CMB result, cosmic microwave background measurement with lambda CDM model, we need a Hubble constant. And it means that by observing cosmic microwave background, we can extract the Hubble constant. And in this case, and the extracted Hubble constant has strong correlation with effective light element that is naively the count of neutrino species and Hubble constant in this way. And the result is given by this way. So Hubble constant is around 66 or 67 in some units, and neutrino species are roughly 3. And in this, in the pure standard model, it is predicted that the neutrino number is roughly 3. Since the summer process, we have to consider effective number of neutrino species not is different from 3, but it is almost 3 here. On the, this is one of the measurement. The other measurement is called direct measurement. And this is the original definition. This is for this measurement, we make use of original definition of Hubble constant here. So the what do you say? Redshift is given by Hubble constant times distance. And by observing distance and redshift, we can extract Hubble constant. In this case, in this measurement, there is no neutrino species is completely irrelevant. So we have only the Hubble constant in this way. This is a result from direct detection, and this is the result from indirect direction. And there is a tension, not the contradiction, but some tension between them. So 2 or 3 sigma tension between their result. So it may be a smoking gun to the new physics. And to to relax the tension, if we have an effective neutrino number higher than 3, that is 3.3 or 3.5, then we can relax the tension. Since the Hubble constant from the CMB goes close to the result of the direct measurement. And this increase of effective number is given by mu minus tau model. in similar to. And this is a result from Escudero et al. And their region is completely same as the previous one. So the mechanism to increase the effective number of neutrinos is that Z prime or Myron can be a stage for neutrino at some history of universe. And since it is a kind of refrigerator, kind of stage for neutrinos, it can increase the effective number of neutrinos. Then, since the effective number of neutrinos is increased, so Hubble tension can be relaxed. And accidentally, the preferred parameter space is same as the ice cube, same as to the parameter region to explain the ice cube gap here. So I was very excited to consider this scenario in more detail. And in a realistic model, I think always there is not only G prime, but also Myron in this kind of models. So we thought that we have to consider whole the process to count the number density of G prime and Myron number density of Myron. And in often they consider only this decay and inverse decay process, and people ignore that this scattering process. Naively, indeed, the scattering process is sub-process indeed. However, in some parameter region, which I will show later, this process can be dominant to count the number density of Myrons. Since Myron is very, in some case, as long as Myron is light enough. The reason I will explain later. But anyway, please keep in mind, in some case, this process is subdominant than this process. So we thought that we have to take into account this scattering process too. But we encounter the T-channel singular process. So sorry, this is taken from the previous paper, and it may not look like T-channel process. Indeed, in the previous paper, we did not realize we are not aware of this is a so-called T-channel singularity. We call this is U-channel process. But whether U-channel or T-channel is just a problem of matter of definition. So this causes indeed a T-channel singularity. Since from this diagram, you can see that G prime decay into two neutrinos here. And one of neutrino can meet at some point to create Myrons. So this is completely same diagram as T-channel singularity. On the other hand, others have no singular type. So kinematically, for example, here neutrino can not be on shell. Also, since neutrinos are very light, here neutrinos cannot be real particle and so on. So that some trouble, if there is a trouble, then this kind of all troubles comes from these diagrams. We can see, yeah. Then in the previous paper, we calculate the this diagram, very brute force way. So as I told you, this neutrino can be real here. So amplitude is divergent as long as we take epsilon to 0 first. Then we discussed how to treat the divergence. And we find, we conclude that this treatment is not established. of course, some people say it is established, but we conclude that it's not established. So we decided to the calculation following the Feynman prescription. That is, we have to maintain the epsilon term here, like in this way, through the calculation. And after all the calculation, we take the limit epsilon to 0. This is the real Feynman prescription. So often we take epsilon to 0 first. But if we follow very strictly the Feynman prescription, we take epsilon goes to 0 finally. So we just follow this prescription. And indeed, even in this kind of calculation, after the integration, we will get divergence which is proportional to 1 over epsilon. However, as I told you, this divergence can be interpreted as a phenomena that in the intermediate state can be a real one. And since such an on-shell term is already included by the decay and inverse decay, so we can remove naively from this divergence term. And then we can get the real off-shell terms for scattering process, which must be considered separately. It's our conclusion. And in the previous paper, we did it numerically. But this kind of singular term causes very cost, calculation cost is quite high in this kind of divergence in this kind of calculation. Indeed, it takes 1 month order to calculate one parameter set. So it's not realistic to make use of. And indeed, in the previous paper, we consider the very limited parameter region, and there, indeed, unfortunately, scattering process is indeed the subdominant. Then why? And then turn to today's main topic. Since we would like to explore for the parameter region, so we need to calculate this divergence more efficiently. However, at first I thought that we could do numerically only, but my student finds that it is very easy to calculate analytically. And indeed, after his discovery, I couldn't understand why we could not find this method. It's so simple. The essence is that always we have to consider this kind of stuff, integrals. And this is, and here we take the divergent part here. And here, so see the these two diagrams here. So this is a T-channel process. And D prime can decay into neutrinos and real neutrinos at divergent part. And this neutrino can hit with other neutrino to create a majoron here. So we take into account, we calculate, we show the example only this divergent part here. And in general, it is easy to see that in general, we have only this kind of divergence integral here. So x is given by the propagator variable. What do you say in English? I'm not sure. So here there is a P3, momentum is given by P3 minus P2. So in the propagator, we have inverse of this parameter here. And Probably in next slide, I will show more details, but here is only essence. And by appropriate changing variable, appropriate change of integral variable, this divergence is always takes this form. And once we have this kind of integral, then it is very easy to calculate. This is a kind of typical mathematics for high school students. So we can calculate here. Of course, arctangent is not a high school student stuff in Japan, but anyway, we can calculate this kind of integral here. So, and the result is very simply given. Note that here we keep epsilon, and after yeah, note that. But anyway, we can calculate the divergence analytically. So let me repeat again. Note that we did not take epsilon to 0 for this integration. Then how to take the epsilon to 0 limit is given by this slide. So anyway, as long as epsilon is finite, not exact 0, then we have a result of the integration in this way. And if AB is how to say, there is no on-shell term inside here, then we have a very simple result. So in each integral have a divergence, but they cancel very clearly. So we do not have to care about the divergence. And we simply have a minus 1, 1 over a minus 1 over b here as a result of integration. On the contrary, if there is a contribution of a real particle in this way, then we have a divergence part. But as I told you, it means in our interpretation, it means that it is an on-shell contribution. So we can subtract analytically this term here. So we also have a result again 1 over a minus 1 over b here. And how to justify the subtraction of this is given by the reason we have to avoid the double counting. So decay and inverse decay and decay process are already taken into other decay and inverse decay process separately. On-shell process is included already by decay and inverse decay process. So we have to remove this on-shell contribution. And let me mention about our application in this calculation. So as I told you, decay, we have to take into account to know the number density of Majorana or Z prime. We have to consider decay and inverse, not only decay and inverse decay, but also scattering process. And to calculate this scattering process, we need this kind of integration. And from here, we have to, and the next line is the result from extracting only t-channel singular contributions in this way. And this integral can be analytically done as long as epsilon is finite. And as I told you, we have to subtract the on-shell contribution and get the final result. So probably this slide has no information for you, but please note that just the fact that we can remove the 1 over epsilon term analytically, and we do not have to we do not need very high computational, numerical computational cost And since we can easily calculate the scattering process, we can check how many myelons are created in the early universe from the scattering process. And to know the number density of particulates, we generally solve this kind of equations. So the time evolution of number density is given by the contribution from expansion of universe and real physical process here. And I will not show the details, but we can calculate inverse decay process and scattering process anyway. And if this creation process are high speed enough, rapid enough, then we will have enough number of myelons. So, and to see this, Gamow gives a very simple criteria. If this rate is faster than Hubble constant, then, for example, in myelon case, myelon is summarized in the early universe. And the result is shown here. So this is a dot line is a inverse decay, the cross section of inverse decay process. On the other hand, this straight line is a cross section for the scattering process here. And as long as we consider the decay and the inverse decay, we have to conclude that since we have to conclude that myelon are not created enough in the early universe. So sorry, this graph is not good. So since myelon is quite light, so as long as it's temperature is high, it is very difficult to create myelons. So inverse decay process means when inverse decay process occurs, it means that always decay process occurs. So the initial two neutrinos are high energy enough, then it is very difficult to create myelon, very large species. So the inverse decay is processed at high energy here. On the other hand, there is no such a limitation in scattering process. So in the early universe, in this scattering process is the dominant. And in some parameter region, as long as we ignore scattering process, we have to conclude that myelon is not summarized. There is no myelon effectively. But by considering scattering process, we can conclude that myelon is summarized in the very early universe here in some process. So we need more careful treatment to consider myelons by introducing a scattering process here. This is today's main point. So we can calculate anyway in this prescription for the official process. And since separately we take into account the on-shell process as a decay and the inverse decay process, we can always compare, we can always consider these two processes. And hence we will get more precise number density of myelons or light particles here. So let me summarize my talk today. So in general, a divergence appears when the intermediate state particle becomes an on-shell state. And as I told you, a certain type diagram, such a divergence is in general regulated by the decay reduce of the intermediate state. While on the other hand, in the T-channel type diagram, the divergence is interesting in sometimes. Since in this in T-channel process, the mediator particle can be stable. In this study, we propose an analytic method to remove the divergence in the T-channel singularity, which has not been regulated previously. The point is we do not introduce any new quantities such as temperature cutoff or beam width. We just follow the Feynman prescription. The meaning of Feynman prescription is given here. So divergence part is divergence has a 1 over epsilon type divergence. What to say? And it must be subtracted since this is separately taken into account as a decay and inverse decay. So in the real scattering part, we have to subtract this 1 over epsilon divergence, and by following Feynman's prescription, indeed we get the finite result analytically. And it makes possible to calculate T-channel scattering in cosmology within realistic time, since we can make it analytically. So we will be able to calculate more precisely precisely in cosmological process. So we would like to apply our method to another in real process in near future. Thank you very much.
So thank